Oh, hi guys, this is Mr. A. I'm going to review the last two properties in our exponents notes and provide some additional examples that will help you learn how to do multi-step problems with exponents in them. So when we last talked, we were going to go over how to deal with negative exponents. So I wanted to provide another example of that and show you how we get that property, because we just barely braced upon that or discussed that at the end of the last in-person session. So here's the idea. I have a problem up here, 7 to the third divided by 7 to the fifth. And of course, by property 2, we would subtract these exponents like so. So we would get 7 to the 3 minus 5. And 3 minus 5 is negative 2. So we'd have 7 to the negative 2 power. Okay, now here's how we can write that using a positive exponent, because the other way to show this is to use expansion. So we'd have 7 times 7 times 7 on the top, and on the bottom we'd have 5 sevens multiplied. 2, 3, 4, 5. Okay. Now, as we know, when you divide a term by itself, the answer is 1. So these 7's here would cancel out. That leaves you with 2 7's on the bottom of this fraction. And what happens then is that this becomes 1 over 7 squared. So by expansion, we also have another value for this expression. We have 7 to the negative 2 here, 1 over 7 squared here. So that means these two expressions must be equal to each other. So in order to write a base with a negative exponent to a base with a positive exponent, we do what we call a swap. We swap the base to the other part of the fraction, okay, like so, right here. And by doing so, then we know from our proof above that that makes the exponent on the base positive. So 1 over 7 squared, just like so, okay? And that also works for variable bases here as well. So if I have x over to the negative 3, that base x goes to the bottom like so, and I have 1 over x to the third. And the reason why there's a 1 in my numerator here and here is because there wasn't other terms in the numerator. So when there's not any other bases left in numerators of fractions, the numerator automatically becomes 1. And something similar then for the when you have a base that's a negative exponent in the denominator, then that base would move to the numerator. So this becomes z to the 6th power. So I'm going to go back to our property notes right here and fill these in one more time so you can understand how these all get filled in. So we're going to start with property 6. So just as we just showed, a to the negative n power would be 1 over a to the n power. And similarly, 1 over a to the negative n power would be a to the positive n power. Okay. For the first example, if the base 19 to the negative 4th power. So if I were to draw a fraction here and move this base to the bottom, it would become 19 to the positive 4th power. And that's how we're able to change bases with negative exponents to positive exponents, because in our answers from this point forward, in your final answers, all the exponents on your bases must be positive. Okay? Now, on the second example, we have a base 2 on the top, but it has a positive 1 exponent, so we're not going to be moving that 2. We are going to move the base x to the top because it's negative on the exponent's negative on bottom. So this is going to become 2x to the 8th power. All right, and that's how we deal with negative exponents. We'll have some more practice on that here in just a couple of minutes. Now, for the next example property where we have a base to a 0 exponent, I'm going to go ahead and say that any base raised to the 0 exponent equals big 1. Base 1, big 1, what have you. And I'm going to now show you how that's the case. We're going to do a problem here where I will show you how you can get 0 as an exponent on a base and then how that becomes automatically 1. So we're going to do 5 to the third over 5 to the third. And again, I'm going to show you 2 ways to prove this is true, just like we did for the negative exponent property. So according to property 2, you can subtract the exponents here. So you get 5 to the 3 minus 3, and that equals 5 to the 0 power. Now, if you expand this out, as we did before, then you'd have 5 times 5 times 5 on your numerator, 5 times 5 times 5 on the denominator. Everything would cancel out, and when you divide something by itself again, you get 1. So since everything canceled out, you'd have 1 over 1, and this would become 1. So then, by default, these two expressions are equivalent. And that's how we're able to prove that any base to the 0 power equals 1. So down here for our examples, 4 to the 0 power, automatically 1. Negative y to the 0 power, automatically 1. 3/4 to the 0 power, automatically 1. Any non-zero base, number or variable, raised to the 0 power equals 1. And that's how that property is done. Now, we're going to go ahead and look at some multi-step examples. Before I do that, I want to show you the strategy guide here that's on the last page of this property notes, okay? So if you could take a look at this with me, and I outline what properties are used for each step of the strategy guide. The strategy guide will work about 95% of the time with all the problems we're going to do. So if you're looking for a surefire, one step, one guide here to do these problems, this is probably going to be your best bet, okay? So for step 1, you're going to take care of any powers outside of parentheses. That's like distributing, okay? Right here, distributing. So this incorporates properties 3, 4, and 5. So just like the order of operations, you take care of any operations within grouping symbols first. We do the same thing here. We try to get rid of any grouping symbols we have in our problem. You do that by distributing exponents outside of groups to all bases inside of groups. Then on number 2, you divide your elements by subtracting the exponents. 3, multiply elements with the same base by adding the exponents. Then it's not until step 4 that we take care of negative exponents, okay? Negative exponents don't get taken care of until step 4. And the reason I put this as step 4 is because by doing steps 1, 2, and 3, and particularly 2 and 3 first, okay, you might eliminate the need to even do step 4, because by adding and subtracting your exponents, you might eliminate them already, because they might add or subtract positive exponents. So instead of having to swap negative exponents once, add or subtract or multiply, and then having to do it again, later on having to swap twice, in this procedure, you only have to do one swap if you have negative exponents by step 4. And then finally, step 5. We change any bases that have an exponent of 0 to 1. Okay, so the 0 property we just learned about, properties number 7. And then if there's anything trivial that we know, like 2 to the third, or 3 squared, or 4 squared, and like similar things like that, and then you just simplify those to a regular base, like 4 squared would be 16, those kinds of things, okay? So now we're going to go look at some examples here. I have those right here for us. And we're going to work about 5 of these. Maybe a chance to work a couple of these on your own, too. So here is the first one. Now, on this problem, there are 3 distinct bases. We have base 3, base x, and base y. So all the numbers count as one base, and then each variable counts as its own base. So when you have a final answer, your final answer should have 3 bases: a number, a base x, and a base y. Okay, so here's the deal. Let's just go through our list of our strategies that I just showed you and see apply which ones to this problem that will help us simplify it. So for example, I don't have any parentheses, so I'm not going to use step 1. I'm going to skip it and go right on to the next step. I don't have any same bases to divide, so step 2 doesn't apply. And I don't have any same bases to multiply, so step 3 doesn't apply. I do, however, have some bases with negative exponents. So the first thing I'm going to do is I'm going to mark the exponent on the 3 as positive 1 so I don't confuse it later on. Because remember, you only swap bases that have negative exponents. So my 3 is going to stay in my numerator for this problem. But the base x will go down to the denominator. The base y will go up to the numerator. So the final answer here is going to be 3y to the 8th all over x to the 4th. And that is my final answer for this problem. All right, all my exponents are positive, and I have one distinct base that I need in my final answer. Okay, I'm going to go ahead now and look at example 2. Okay, in example 2, again, it's another exercise in just working with the negative exponents again. First thing I'm going to do is make any invisible exponent 1s visible. So this base c has a c to the first power. So I'm going to put that on our base c, and I'm going to start doing some swaps because I don't have any grouping symbols to take care of. I don't have any bases to divide, any like bases to multiply. So I'm going to move base a to the bottom. I'm going to move base b to the bottom, and I'm going to move base d to the top. Base c is going to stay on the bottom because it's raised to a positive exponent. So I'm going to pause for a second and allow you guys to hit the pause button and get your final answer before I move on. Okay, so here's what we're going to do. I'm going to move my d up to the numerator. So I'm going to have d to the third power on the numerator. Go ahead and draw my fraction bar here. And underneath that, I'm going to have a squared, b to the first, and then c to the first. And then we usually write the variable bases in alphabetical order in our final answer. So then this answer is done. Let's move on to example 3. Now in example 3, we start incorporating some different properties. And we're going to have to start doing some multi-step type of things, okay? So first thing I'm going to do is identify that the exponent on the base 7 is 1 and the exponent on the base 5 is 1. And I'm going to start going through my steps. My first one again is, do I need to distribute any exponents? The answer is no, because I don't have any single exponents outside of grouping symbols. Step 2, do I need to divide any powers with the same base? No, because I don't have any division in this problem. So the next step, though, is do I need to multiply any bases with this, or exponents with the same base? And the answer is yes. So here's what we're going to do. I can multiply all numerical bases as long as they're raised to the first power. So I'm going to multiply 7 times 5 right here. I'm going to get 35. Okay, and I'm going to do the same thing, the x to the 4th and the x to the 9th. I'm going to add those exponents. So I'm going to get 35x to the 13th power. And that's my final answer. All right, now for the next example, I'm going to try to give you guys a chance here to maybe start working on some of these things on your own. So why don't you, I'm going to pause a minute and I'll give you a chance to try this one on your own, and then I'll catch you on the other side of the pause. So go ahead and hit your pause button for a minute and attempt this problem on your own, and then I will chat about it and solve it on the other side of the pause. Okay, so this one is interesting because it involves a few additional properties. So here's what we're going to do. We have a base u and a base v. So what we're going to do is, first of all, I have an exponent outside of a group this time, and I'm going to distribute it to the bases inside the group. So this 3 on the outside gets distributed to the u and the v only in the second grouping, because there's an exponent of 1 on the first grouping. So you only distribute exponents to the bases immediately inside the group. Not to every group, just the ones that are inside the immediate group, okay? So I'm going to go ahead and write down the first grouping. So u to the negative 5 v to the fourth. That stays the same. And now I'm going to distribute. So negative u to the ninth and v to the negative sixth. All right? And we're not going to have to do any dividing, so we're going to go right ahead and do our multiplying. And I can multiply the u bases together because these are just coefficients. So I have a positive 1 theoretically there and a negative 1 theoretically there. That's going to become negative 1 when I multiply those u's together. And I'm going to do that still by adding the exponents together. And I'm going to do the same thing here with the v's. Okay. So then negative 5 plus 9 is going to be 4. So I'm going to have negative u to the fourth power, and then 4 plus negative 6 is negative 2, v to the negative 2 power. And then I have to take care of any exponents that are still negative. So base v has a negative exponent, so I'm going to draw a fraction bar, move base v to the bottom. So my final answer for this one is going to be negative u to the fourth power over v squared. And that's how we simplify that one. All right, for our final problem, it looks daunting, but it really isn't. So we just have a lot of subtraction to do on this one, and a few other things to take care of as well. So we have 4 bases. We have a numerical base, we have an x base, a y base, and a z base. So I need to do subtraction here, here, and here, okay? And subtract those 2 exponents, those, and those. And then I also need to divide these numerical bases. They're both raised to the first power, so you just multiply or divide those normally as the problem indicates. So I'm going to have a 4 in my answer, okay? And I have 5 minus negative 2. Let's just write this over here to the side so we don't mess up our subtraction. So 5 minus negative 2, and I have negative 3 minus 8, and then I have 4 minus 4. So that's going to be for x, this is for y, this is for z. And change your signs accordingly. Double negative becomes a positive. And this becomes a plus a negative 8. And then, of course, 4 minus 4 will be easy to do. So I have x to the 7th, y to the negative 11th, and z to the 0 power. I'm going to pause for a minute and let you guys finish this problem. Okay, so the first thing we need to do, there's actually 2 steps to go. So the first thing we need to do is move base y to the bottom of our fraction because it has a negative exponent. So I'm going to have 4x to the 7th, z to the 0 power, over y to the 11th power. Now, we know that any base to the 0 power equals 1. So the z to the 0 power does indeed equal 1. So this is going to become like multiplying by 1. So it'd be 4 times x to the 7th times 1. And we know that multiplying by 1 is a redundancy. So our final answer for this problem is going to be 4x to the 7th over y to the 11th. And that's going to be the final answer for the final problem. So I hope this helped out a little bit as you guys complete your notes and your examples. And if next time we are together, we'll review this real quickly, make sure there's not any other additional questions or concerns, all right? All right, thanks, and I'll see you soon. Take care.